It's like a reciprocating compressor, although on a much smaller size. This is generally what it's going to look like. Again, the shaft here, the inlet header through the pistons, and then out the discharge header. On these pumps, we generally are going to try to connect them so that the suction is on the bottom, so that as you flood them with fluid, the gases automatically migrate to the top and out, rather than try to have them go the other way like we do on a compressor. Positive displacement, the reciprocating pumps, they also impart pulsations into the fluid stream. They can supply very high pressures with very low flow rates. They're not tolerant of solids in the liquid at all. They have a fixed flow rate unless you have a variable speed driver, and they're self-priming for short durations. In order to prime a pump that is not a self-priming system, basically if you can't pull a vacuum or if you can't supply a priming liquid, you're asking the pump to act as a compressor to evacuate all the vapor that's in the suction line until the fluid gets pulled up to it. So when you've got a reciprocating pump, it'll be able to do that for a short while because it's got very tight tolerance clearances, and it'll be able to pull gases for a little while. But it does build up a lot of heat doing that, and you will see additional wear on the cylinders when that happens. Diaphragm pumps. They use air as driver for the most part. Occasionally you'll find some that have a motor drive. Those are kind of a very specialized application that's considered high pressure for a diaphragm pump. They're good at low flow and low heads because since they use air as a driver, the discharge pressure can't be any higher than the air pressure that's being supplied to it. Since most instrument air and utility air systems are designed to run between 80 and 120 psi, that's going to be around the discharge pressure that you can expect out of a diaphragm pump. They're very inexpensive. They don't have any motors, they don't have any turbines. You just have to supply air to them to make them run. They can run dry, which means that if you hook them up to a liquid source and you pump it until the liquid source is gone, they won't be damaged if they're just pumping air back and forth internally. And because of that, they are self-priming. Generally, the diaphragm-style pumps, we use them in sump service, building sumps, module sumps, when you're pulling liquids of various compositions out of a pit and then trying to put them into a low-pressure header someplace, usually for disposal. Gear-type pumps. There's a couple different styles. The first is the counter-rotating setup, where the liquid comes in, gets passed around the outside, and then pushed out the discharge. And then the other one is where you have rotation in the same direction with two different sized cavities in order to get the flow rate that you're after. We'll use these in extremely low flow, high head applications. Sometimes you see them with a double helical or a herringbone style of gear design. Again, it's a low flow, moderate head to high head application because it is a positive displacement pump. Efficiencies are dependent on how accurately the machining is done along the side, the face of the gear and the casing that it's being contained in. Again, it's not tolerant of solids, and because there's interaction between the gears, it's really not suitable for fluids with no lubricity. It's a fixed flow rate, again, without a variable speed driver, and they can be self-priming to a certain extent. And a screw-type pump. It's got a male helix and a female helix. Fluid comes into suction and gets pushed along towards the discharge, and then it's pushed out the discharge orifice. This one is a axial flow inlet outlet. This one is a side flow inlet outlet where the fluid comes in off of the side, is ducted to the front of the helix, pushed to the discharge side, and then sent out. We use these a lot in lube oil services for our oil system skids to support larger pieces of equipment. They have very good reliability and they are self-priming. For a reasonable length of time. They won't run dry well because you do have contact between the helixes, and so if you try to run them for a long period of time, you will start having some wear across the faces, opening up clearances and reducing your efficiency. Then you have a progressive cavity pump. It's an interesting style pump. There's one moving part, which is an interesting helical shaped rotor, and then it has a similar shaped stator section, and what it does is it just has a cavity that kind of moves from one end to the other, and it grabs a chunk of fluid and pushes it out, pushes it along, and then pushes it out the discharge. If you have a fluid that you don't want to have sheared or broken up, say you have a separator where you're trying to separate water and oil, but you need to pump it now as a combined fluid, but you don't want to break the oil up into an emulsion inside the water, you would use this style of pump because it's very gentle to the pumpage, whereas a centrifugal compressor, you have huge velocity changes. It's going to shear all of the liquid inside and turn it into a homogeneous fluid out the discharge. So if you've got things that that you're trying to separate and you don't want recombined again, this is the pump that you would select. Again, we use them for oil systems, but they can be used if you've got oil and water separation services. Only one moving part, and so because of that, they've got really good reliability. They're very intolerant of solids because their ability to operate is based on tight clearances between the rotor and the stator. So any kind of a solid that might get inside and wear those tolerances out will reduce the ability for the pump to operate. Metering pumps. These are very accurate volumetric pumps, and they will repeatedly put out the exact same volume each stroke. They're a positive displacement pump, usually a piston style. And when you have chemicals that you need to add repeatedly in an accurate method, these are the pumps that you would select. They have manual and automatic adjustments on them, so you can adjust the amount of chemical that you want injected into your fluid stream. They'll generate very high pressures with very low flow rates. Several thousand psi is not unusual if that's what it takes to get the chemical into the process stream. Normally we get these as a package, which will come with an instrument section, a tank, and maybe even controls for flow and on-off protection. They're self-priming. This is what they look like. You've got a motor into a gearbox, which runs a set of gears. At one location, you've got a vernier screw, which allows you to adjust the piston stroke. And so you can adjust the flow rate. Usually there's a 10-to-1 turn-down ratio, and in some cases we can get 100-to-1. Yeah, we can get 100-to-1 turn-down capability. The fluid would generally enter through the bottom. There's a check valve, and then a piston back and forth slowly pulls liquid in and then pushes it out the discharge. So this is what they look like internally. You've got a worm gear driving a spur gear, and by adjusting the radius that the connecting rod connects to the spur gear, you can adjust the stroke length of the piston. Obviously, if the pivot point is right at the center, there's no motion at all, and as you go out towards the OD, the motion increases to a maximum. And when we buy them as skids, the pumps right here, we get pulsation dampers. Sometimes those are required. Lots of instrumentation for monitoring pressure, flow rate, temperatures in order to make it an automatic system. Sometimes we'll buy them with the tank mounted on the skid that it pulls its fluid source from. Other times, if the tanks are extremely large, or if it makes sense to buy them ourselves because of an odd location or an odd requirement for materials. We'll do that, and then we'll just pipe the tank to the skid. So some new developments. These are new in our industry. They're coming along. You're probably going to run into them during your careers. The first one is a multi-phase pump. And this one is capable of moving both liquids and gases at the same time. And previously that was kind of unheard of. You either separated the fluids apart, and then you would compress the gas and pump the liquid. Now you're trying to do both at the same time. And there's two styles that are currently under development and under consideration. And the first one is basically it's a screw setup where your fluid is going to come in from one section, be brought to the outside of the screws and get trapped between them, and gets pushed along the helix into the center section where it is discharged. We haven't had a whole lot of experience with these. We're kind of seeing how they're going to work. They seem to be pretty popular right now with platforms in the North Sea, where rather than have the separation service on the platform, where real estate's very expensive, this is used to push just the basic stream of gas, oil, and water as it comes out of the well through pipelines to shore, where they can go through the separation process at a much lower cost. This is what they're looking like right now. You can see the sectional view showing the helixes inside. Very precise machining, very close tolerances. It's a very interesting pump. The other form is an axial flow machine, where you come in at one end and you are pushed towards the other. And it's an interesting set. There is a similar helix. It's a kind of a screw that is on the shaft that rotates, and each section then goes into a stator section which straightens the flow out so that it can be properly angled for an angle of attack of the screw section on the next stage. So it's a rotating section followed by a stator section, then a rotating section. And here's a set of stator sections. So that's a new development. We're not sure how it's going to go, but it's kind of interesting to watch and see where it goes to, and see if we can start using that in our industry as well. Next one is called the downhole pumps. We talked about that a little earlier in the day. It's a new form of oil lift. Right now, oil lift is done by injecting gas down into the wells, and the gas is used to help bubble the oil to the surface. But areas where they don't have gas for that kind of injection, but they don't have enough pressure inside the field to push the oil up to the surface, the alternative is to put a downhole pump down in the bottom of the well, however deep that may be, and then run it and pull the oil and water up that way. That's even more recent than the dual phase. Right now, BP's got some experiments going on, and they told me that they're actually running about 50% reliability. And the real problem is whenever there's a power failure, all these pumps shut down. When they try to restart them again, only about half of them actually restart. So that means you have to pull the pump all the way out of the well up to the surface so you can do some work on it. And these wells are 3,000 foot deep, and so you've got to pull 3,000 foot of power cable and piping out to be able to get to the pump, so you can break the broken wire that's in the motor, and then you can go ahead and drop it back down again. So access for these is a real problem. But the nice thing about them is that they require very little infrastructure. You don't need a module, you don't need a building, you don't need a doghouse, you don't need anything except a hole in the ground to stick them in. It's going to replace the gas lift, so if there's no gas around to act as gas lift, this is one way of getting additional oil recovery. So that's what they look like. Extremely thin. The motors are extremely long to be able to generate the torque to make it while keeping it within a package that you can actually drop down inside a well. So, pump seals. Most every pump has to have a seal. And what you see here are the external seals of the secondary sealing system. Right now, seals are used to keep the pumpage inside the pump. And the type of seal varies depending on the pumpage characteristics of what we're dealing with. If it's water, it'd be a single seal, not well instrumented. If it leaks, it's okay, it's just water. If it's a hydrocarbon, we would use double seals. If it's a toxic gas, we also have double seals, but with extra instrumentation to monitor the health of the seal. The type of seal that we select also may depend on the local codes. Los Angeles County will require a different sealing system than Tulsa, Oklahoma may require because of the fugitive emission requirements that the AQMD imposes on facilities in the area. Right now, our industry has been moving towards double seals to minimize fugitive emissions along the pump shafts. And so the pumps have quite a few different alternative sealing systems available to them, going from a very simple just put a packing in and let the pumpage leak out to the ground. If it's a water, that doesn't matter, it's okay, to more sophisticated single seals, which are used to, if your pumpage is somewhat expensive but not environmentally hazardous, then you would want to keep as much of it inside the pump as you can, and so you would use a single seal to minimize leakage to the atmosphere. If you have hot liquids in your pumpage, then you would put a heat exchanger in some of the seal systems. If you've got a slurry or if you may have particulates, you may want to put a cyclone separator inside to be able to get all of those particles out of the pumpage before you put it back into your seal system. But there's quite a few, and we end up picking them based on, like we were saying, the local code requirements or environmental restrictions or client preference or what we think would work best for the pumpage and the application that we're looking at. Right now, the vast majority of the seals that we're putting in our industry are a double seal, a Plan 11, and a Plan 52. And what the Plan 11 does is it takes pumpage from the discharge of the pump and then flushes it through across the inside surface of the primary seal. And what that does is it keeps the seals cool, and it also helps to flush any dirt or particulate buildup that may be happening inside this chamber back into the pumpage stream so it can be removed from the pump. Now, these seals are very similar to compressor seals in that they are very tight tolerance, but they are actually not touching. So there's a small gap between the two, and so there's a small amount of liquid that's going to pass across the face of the seal. And as it passes across the face of the seal, it picks up the heat of friction generated. And so generally, once it gets on the other side of the seal face into the inner seal chamber, it's flashed off into a gas. And so that gas will head out to the flare system through the Plan 52 discharge. And that Plan 52 signifies that we have a secondary seal that's basically identical to the first one. And then we have a fluid that runs between the two that circulates around, keeps this seal cool, lubricates these faces, and it forces the gas that flashes off of the pumpage, the process pumpage, out into a reservoir, and that's connected to the flare system so that any fugitive gas emissions goes off to the flare and not across the secondary seal face and out to the atmosphere. One of the other alternatives that we have is we have the same Plan 11 that flushes the inner seal face, but then we have what's known as a Plan 61, which is actually a secondary seal that cools the inside, and if any gas comes in from this direction, is trapped inside the system that services the Plan 61. So the idea is to minimize and hopefully prohibit any pumpage, any leakage from the pumpage of escaping to the atmosphere.
What type of pump is good for handling toxic chemicals?
Well, what type of pump is going to be dependent upon what head and what flow rate you're dealing with. Okay, because for example, a centrifugal pump is perfectly fine for a toxic service if we put the right seal on it.
Centrifugal pump, they have high leakage.
That's not necessarily true. You would not try to put a recip into a high flow condition simply because you would be running it so fast that you would have huge wear in the piston, which would actually allow your pumpage to leak past the piston in the crankcase, which is vented to atmosphere. So you wouldn't have positive containment under those circumstances. So we would pick the pump based on the process, and then we would select the seal based on the severity of what would happen if your pumpage leaked out to atmosphere. So we've had really good luck with this 1152. Whenever we've had basically zero fugitive emission requirements that we have to meet, this has been doing very, very well for us.
Those are external settings, those sealing.
These physically sit, this section here, this is the actual seal cartridge, and that sits right on the pump shaft. All right, and then the Plan 11, let me see if I can find that, has a pipe that comes off of the pump discharge through an orifice to restrict the flow rate, and then it's sent right into the seal, the inner seal, to flush that inner seal. So this is contained all within the pump, so there's no leakage here. And then the Plan 52, you'll see it here, it's got a reservoir that holds a benign process fluid, but that has good lubricity to lubricate the seal faces. And when pumpage leaks across the inner seal face, it flashes and actually ends up in this reservoir. And then from here it goes out to our flare system, so that also will not escape the atmosphere. It gets burned up in the flare. So because of these two, because of the Plan 11 and the Plan 52, we can pretty much meet, well, we can meet the LA AQMD requirements for fugitive emissions off of the pumps. So that would be it for pumps and seals. If you'll give me about 5 minutes, I'll swap over to the balance of the plant. Well, we're 15 minutes ahead of schedule. Oh, it's going to have a break at 5:20 and restart at 5:30. I know it's a little early, but go ahead and we'll just restart at 5:30, put it back right on schedule.